receive very large corrections as we approach the breakdown scale. Previously, the mass had a bit of a pathological issue, which was that the energy that the black hole had above extremality could be smaller than the energy of a single emitted Hawking quantum. And that would be bad because the black hole wouldn't be able to radiate. This was resolved by this correction that came from the one loop. Well, it's exact. The correction is one loop exact, but it's a one loop computation around the near extremal black hole. Similar for the entropy, we saw that the entropy as it approaches extremality also receives a large correction that has the same origin. This logarithmic term can become more important than the linear term when P over M break becomes order 1, and eventually S of T decreases well below S naught. The regime up to where we trust these results is up to temperatures that are non-perturbatively small in 1 over g Newton. So T going like e to the minus 1 over g Newton. Right. So I will provide two other derivations of the same result. It's always good to convince yourself of a result in different ways. And we'll see that in these two other derivations, we'll gain a little bit of more physical intuition about what's happening and about how universal these results actually are. So derivation. Is similar in spirit to something that some of you might have seen before, which are the derivation of logarithmic and area corrections to the black hole entropy. So similar, and this was derived throughout the 2000s by Ashok Sen. Namely, what Ashok and his collaborators did is that they started out with the extremal black hole in the near horizon region. As we saw at exactly extremality, the metric was ADS2 times S2, where for the purpose of the derivation that I'm about to give, it's convenient to parameterize ADS2 on the Poincaré disk. And the solution has a gauge field turned on that looks like Q cosh rho minus 1 times ct theta. This is the an electric black hole. And what Ashok and collaborators did is that they just took this metric and expanded it to first order imperturbation theory. And the same for the gauge field. So these are quantum corrections. Also, sorry, that's a Koch. I missed the H. And you could consider not only gravity and electromagnetism, but you can consider a variety of other fields, such as scalar fields or for many other fermionic fields. And we can consider the type of fluctuations for them on this very specific background. Great. So this is very similar to what we did in the previous derivation in JP gravity. The difference being that there we were able to isolate the modes that we thought were important in the metric. namely these fluctuations that change the shape of the boundary of the near horizon region. So the purpose of this new derivation will be to understand why these modes were not previously seen at extremality, or whether they were seen treated in an improper fashion. Okay, so what people did is they started by considering, by expanding the action, the Einstein-Maxwell plus matter.
2020 Dubai, Omar Iran, across the decades on YouTube Music.
Into the on-shell action, that's in terms of G and A. Plus the action at quadratic order in terms of the fluctuations. Yeah.
Here it's important that also your additional fields psi or the background is all fixed by the attractor mechanism in terms of Q, or can you consider
the background is the attractor. It's just for the purposes of this calculation, it's just important that it's ADS 2 times an internal manifold.
But you don't care about the background value of psi, right?
No, I don't care about the background value of psi. For the purposes of this exercise, the exercise I'm imagining here, right? Previously, we obtained the result for Einstein-Maxwell theory. Here, we imagine that we have Einstein-Maxwell theory. It has a Reinstein-Nordstrom solution that has no vevs or any of the scalars, and then we expand around this background. So psi is equal to 0 on the background that I'm choosing. I could also expand around the attractor solution if I study supergravity. But that's a detail that for now I'll omit. I will discuss a little bit how these results generalize to theories of supergravity in a second. So there, the quadratic expansion of these modes can always be put in the following form. I can form a vector of all these fields, H, A tilde of psi, H, A tilde of psi. This is schematic. And I can find a differential operator that such that my quadratic part of the action takes this form. For instance, many of you are probably accustomed to writing a scalar action in terms of psi Laplacian psi. But in principle, there could be off-diagonal components that couple different modes of different fields. So in principle, this D is some general differential operator that contains off-diagonal mixtures. And it turns out that all the modes, all the eigenfunctions of this differential operator can be constructed in one way or another from the eigenfunction of a scalar field under the Laplacian of ADS 2 times S2. So if I try to solve the equation minus Laplacian of U equals K lambda L Q lambda N L, I find the following set of solutions. I find that Q of lambda P L and M. So for each lambda and L, I find an entire series of solutions labeled by P and M. You will recognize, due to the S2, exactly what's happening in a second. I find that it's given by YLM theta phi times some function f lambda T rho and tau, where these are spherical harmonics these are essentially the equivalent of spherical harmonics on hyperbolic space. They're just eigenfunctions of the Laplacian on ADS. So we can call them hyperbolic harmonics. L labels the spin, and lambda labels the SL2R representation of each one of these modes. Here, the scalars are normalizable when considering lambda to be in a continuous series representation of SL2R. The eigenvalue that you get, I won't try the exact eigenfunctions, but they're easy to find on Wikipedia or in Mathematica. The eigenvalue k as a function of lambda and L, well, one part, so it scales like 1 over q squared, because that's the thing that enters the radius of ADS2 and the radius of hyperbolic space, times L plus 1. I'm sure all of you recognize this as the eigenvalue of a Laplacian on a sphere, plus a quarter times lambda squared. Scalars turn out to not couple to anything except to the Laplacian of the background metric. And therefore, one in principle can use these eigenvalues to compute what the one-loop determinant of a scalar is. So one can compute what determinant of nabla to the 1/2 gives you. The way in which one can compute them is using a heat kernel method, which expresses is a nice way to regularize, if you know the eigenvalues of the differential operator, in this case the Laplacian of the scalar, it's a nice way to regularize the result such that you get the determinant of the Laplacian. And in this case, you just get the only scale that appears in the problem is the thing that appears in front of the eigenvalue itself, which is this q. So the overall answer that you get for the determinant of a scalar is q to some power. For one scalar, you get that this power is minus 1 over 180. Not that important. It's just some power of q. Great. Good. So we can start computing heat kernels for this differential operator. But when you do a heat kernel computation, there's oftentimes one subtlety, which is that sometimes on manifolds with boundary, especially, but also that, but on manifolds with boundary, what oftentimes happens is that somehow sometimes you encounter eigenvalues of D that are 0. So these would be 0 modes of the action. So 0 modes are important quantum mechanically because in principle there's nothing that suppresses in the path integral over such modes. There's nothing that suppresses their fluctuations. In principle, when you have exact 0 modes of the action, you have to do a full path integral over the specific modes that you identified as your 0 modes. So the question then is, what are the modes that are actually 0 modes of this differential operator B? And people actually answered this question. And they were found to be largely theomorphisms and large gauge transformations. So it's largely theomorphisms of the metric and large gauge transformations of the fluctuating gauge fields that I'm considering, of the gauge field quantum fluctuations. Great. So let's start with the simplest example of the 0 modes that I'm sure we will all identify, which are large gauge transformations. For E1. And these are given if we insert A, so the curly A, the quantum fluctuation of the gauge field to be d lambda, with lambda equals sum from n greater or equal than 1, a n, 1 over square root of 2 pi n, in rho, divided by 1 plus cosh rho to the n, e to the I n tau. One finds that this is an eigenfunction, that this mode is an eigenfunction of this differential operator with eigenvalue 0. And you might say, well, of course, it's a gauge transformation. It's a pure gauge transformation. It's d lambda. Why are you even integrating over that? Aren't we quotienting our path integral over configurations of the gauge field by gauge transformations? Well, we should do that, but we should not quotient that path integral by gauge transformations that are large. In other words, by gauge transformations whose gauge parameter does not vanish as we approach the boundary. So here, notice that as we take lambda, as we take rho to infinity, this ratio between sinh rho and cosh rho goes to 1. So at large rho, this gauge parameter does not vanish. And for instance, if you remember, when I wrote the electromagnetic boundary term all the way back in lecture 1, in the Gibbons-Hawking, the electromagnetic boundary term needed to satisfy the variational principle. When I fix the field strength, the boundary term in that case looks like integral of a mu f mu and nu. So, for instance, one effect that these gauge transformations, large gauge transformations, have are that they make my boundary term change. They have non-zero, depending on the situation, they might have non-zero activity. And also, they can lead to physically distinct configurations. So, the important thing why we didn't encounter, in some sense, these modes for scalars is that this gauge parameter can be viewed as one of the scalar modes. But for scalars, I'm interested in functions that in eigenfunctions that decay when they go to the boundary of ADS2. While here, since I act with a derivative on lambda, the A itself can decay as I go to the boundary of ADS2, but the gauge parameter itself might not have to decay in order for A to be a normalizable mode. So this is one set of zero modes. And there are other two sets of zero modes of the metric, in this case. One that corresponds to rotations of the background. And these can be written as h mu alpha equal a sum from n greater or equal than 1 sum over m 0 1 of what's essentially p alpha beta p beta equal 1 m beta phi times a derivative of exactly the same type of potential the same type of gauge parameter that I wrote above. So you take this value of lambda, give it an index m, or m going through -1, 0, and 1, and you can generate large diffeomorphism of the metric that physically corresponds to the black hole slightly rotating if I go around the boundary of ADS2. So here, as I go around the boundary of ADS2, what happens is that the h mu alpha changes. And changes in h mu alpha can be viewed as inducing a rotation for the black hole that I'm talking about. Good?
This is a different parameter than one used.
Yes. So here, lambda m, each here, lambda I, yeah, so here the gauge transformation I just parameterized by lambda. But here I just mean that lambda m is equal to a sum over n bigger or equal than 1. There's no sum here. Sum n bigger over n bigger or equal than 1, a n m. But exactly the same formula is put in here. And the reason why these formulas are so similar, by the way, is that one way to view rotations in this black hole background is that when you do you're turning on a non-trivial background for an SU2 gauge field, where the SU2 gauge field is what arises when you do a dimensional reduction on a sphere. So when you do a dimensional reduction on a sphere, in general, from the dimensional reduction, you get a gauge field that captures the internal isometry of the sphere. So that's why in ADS5 process 5, there's an SO6 gauge field that captures the isometry of S5. In the same way here, when you do a dimensional reduction, there is an SO3 or SU2 gauge field that captures the isometry of S2. And this h mu alpha is just the way in which you're relating that gauge field to fluctuations of the metric. Specifically, these guys are killing vectors of S2. You can check this. They satisfy the killing equations on S2. It's a fun fact about spherical harmonics that this is the way to get killing vectors.
Look, your toilet is open, the right one.
Oh, thank you.
That's how physicists get accidents. So.
I think they could get accidents in many different ways.
While working. Paper
Yes.
cuts and shoelaces.
Right. So these are actual killing vectors on S2. So they satisfy their Lie algebra satisfies the same as an SU2 algebra, and this entire thing can be viewed as a large gauge transformation for the SU2 gauge field, which in terms of the metric is just a large diffeomorphism of this specific component of the metric. And finally, there is another zero mode, which corresponds to boundary fluctuations. Oh, perhaps it's important here that mu, I should mention, in case the notation was unclear, mu labels either the radial, either labels the radial, rho, or time direction, while alpha labels coordinates, one of the two coordinates of the sphere. That's why it's a rotation. And if you guys remember anything about Kerr black holes or Kerr metrics, is that they have a component of the metric that looks like d tau d phi. And that's what causes the black hole to rotate. Anyway, so now if we look at the final type of zero mode that people encounter for the differential operator, it's a transformation that only involves components of the metric that are either rho or tau. So here, the form that people found for the zero mode is that you sum over all n and z with n bigger or n strictly bigger than 1, 2n times n squared minus 1, I epsilon n, e to the I n tau, tanh the n rho, e rho squared over sinh squared rho, plus d rho d tau, rho, minus d tau squared. So this is a complicated, seemingly a very complicated transformation of the metric, but it just has the property that it's mapped with the necessary differential operator that appears in the action on this specific, sum. You always get 0 for any choice of exponents. So all these, this specific transformation, one can actually write as a diffeomorphism of the metric. So this diffeomorphism is generated by the following vector, which is a sum from n greater or equal than 2, epsilon n, e to the I n tau, tanh to the n rho over 2, I n plus cos rho divided by sinh rho, d rho, minus n plus cos rho, plus rho. I'm almost done writing complicated formulas, so bear with me. Divided by sinh squared rho, d rho, d tau. So what's important to notice here is just like before for gauge transformations, when we took rho to infinity, we saw that the gauge parameter does not vanish. This is a vector, right? It's it has derivatives, right? So it's a vector field in ADS2. And if I take the limit rho going to infinity, I see that this vector is still non-vanishing all the way at infinity. So that's why it's a large diffeomorphism. It acts non-trivially when I send rho to infinity, both on the rho and on the tau.
Is that a tanh rho there? In the first
Tanh.
Yeah, sorry. Thank you. I keep missing H's.
And so, if we were to repeat all of this for 3 dimensions, these would become Virasoro deformation?
Yeah. Yeah.
And your,
in ADS3.
Your S3 gauge field would be, your SU2 gauge field would be a U1 gauge field.
Up above.
Right. Killing vectors,
Yeah.
that's one.
Yeah, exactly.
Sorry, but I thought, so the number of the types of zero modes that you have for the Dow inversion on ADS is highly dependent on the dimension, and in particular on generic ADS-D.
Yes, on generic, but
D/2 forms that have zero modes
Yes.
and things like that. So in 3 dimension,
in 3 dimensions, I think it's because you can write things as SL2R times SL2R. And essentially,
okay, but if I go
copies of these.
if I go to 4 dimensions,
Yeah,
it's really a different set of zero modes, and it can be.
Okay, so let me just get to the point, which is that if we send rho to infinity, I just becomes epsilon prime of tau. These epsilon n's can just be identified as a Fourier modes of a function, this epsilon prime, the rho minus epsilon tau d tau. Okay, so maybe this already starts looking a little bit familiar, because let's compare this to what we would have done if we would have tried to describe the fluctuation of an ADS2 boundary in these rho tau coordinates. So in that case, we would try to, as we did before, fix the induced boundary on the metric. So row boundary just labels where I put my cutoff. So row boundary is very large. And f of tau I can parameterize as tau minus epsilon of tau.
Can you just repeat what are we doing now?
Now I'm just comparing this large diffeomorphism to what would I'm trying to identify this large diffeomorphism with precisely the modes that become the JT modes in the near extremal limit. So how we found the JT mode is that we solved for the metric, and this constrains what rho is as a function of this function f, right? So if f of tau is parametrized by tau minus some epsilon of tau, then rho of tau just becomes rho critical minus epsilon prime of tau plus order epsilon squared. If I just plug this back into this equation and solve for rho of tau.
So how did rho become a function of tau?
So here I'm thinking of a boundary being described by a proper boundary time, which is tau. And by it's describing a curve that's labeled by a function rho of tau and f of tau. So I have an ADS2 space-time in Poincare coordinates, and I'm just considering some arbitrary curve along which the induced metric is fixed to a constant. So this is the induced metric fixed to a constant, and my rho and tau are being described by, maybe it's a poor choice of variables. Perhaps I should write it as rho of u.
What I'm confused about is you're starting off with some fixed ADS2.
Yes.
And thinking about this family of diffeomorphisms that not large, they're diffeomorphisms that don't decay fast.
Yes, so they don't change the Ricci scalar of the space-time because they're diffeomorphisms, but they affect properties of the boundary of the space-time. So now I'm trying to map, instead of thinking about...
In your original coordinates, the boundary was at some fixed rho, is that right?
In my original coordinates, let's say the boundary was... Yes. Yeah. Let's say it's at some fixed rho. And then I perform a diffeomorphism, and the boundary is transformed by the fact that the metric changes.
Okay.
So now I want to, in some sense, do a diffeomorphism again on this new metric or rather, we can think about active versus passive transformations. And I can think about keeping the metric fixed in this patch, but allowing this boundary curve to vary. And I just want to find the map between this large diffeomorphisms and the fluctuations of the boundary curve in a case where I keep the metric fixed. Okay. Does that answer your question?
Yes.
Okay. Yeah, thank you.
We're just going to be clear, you're telling new coordinates.
Yes. Well, it's the same coordinate system because I'm just keeping my initial metric, but I'm changing the location of the boundary. Good. So this is the way in which the location of the boundary is described. What the location of the boundary is described by? It's described by this function epsilon of t, and rho of t is described by this function epsilon prime. which if you take the limit rho going to infinity, it precisely identifies this parameter epsilon in this transformation with the parameter epsilon that parametrizes the shape of the curve in the coordinate system where the metric is kept to a constant. So essentially, the meaning of this zero mode is precisely the same as the JT mode, the Schwarzian mode that we saw earlier. Epsilon of t, which parametrized the shape of the boundary, was the Schwarzian mode. And the reason why it's a zero mode now is because we saw at the beginning in the last lecture that the coefficient of the Schwarzian, the coupling of the Schwarzian that appeared in the action was precisely T coupling of Schwarzian, was precisely given by the ratio between T and the breakdown scale. So as I take the exactly extremal limit to consider the space being purely ADS2 times S2, this ratio goes to 0, which means that all these modes epsilon of t don't have any weight in the action. And that's the definition of a zero mode. That's why on ADS2 times S2, so no fluctuating sphere size, epsilon of t is equal to a zero mode. And you could actually see, identify exactly why we're summing here from n bigger than 1. The modes that correspond to n equals 0, 1, and minus 1 correspond simply to SL2R transformations that are just isometries of the space-time, so they don't actually change the space-time in any physical way. Therefore, they shouldn't be considered as large diffeomorphisms. Okay, great. So we've mapped. Yep.
If I have a spin through, then there are other zero modes, right?
Yes. If you have a spin-free half, then there are all the zero modes. I'll discuss them in the second part of today's lecture. So now, in principle, if you did your one-loop determinant of your differential operator D, it wouldn't be correct to do a one-loop determinant due to the zero modes. You could only account for the modes that are not zero. So you're left, if I integrate out all modes to quadratic orders except for the zero modes, you're left with q to some power, d log, that I'll write down in a second what it is. And you're left over with an integral over d psi, the epsilon, d little a, and d little a at a m. So this one corresponded to boundary fluctuations, boundary shape fluctuations. This one corresponded to fluctuations of the gauge field. And the final one corresponded to fluctuations of the angular velocity. And in principle, the fact that we see that this mode appears in the Schwarzian, that's an exact statement. It's not only for infinitesimal epsilon. Shows that that mode is actually a zero mode to all orders in epsilon in this action. So it's not as if it's suppressed by e to the minus epsilon to the fourth. It's not that it's just a zero mode in quadratic order. It happens to be a zero mode to all orders in epsilon. And the same can be actually shown for the variable little a and the variable little am. So there's no term like this. So the conclusion is that to actually do this path integral properly, one would have to do the path integral over these modes explicitly. One might wonder whether, this number is an order 1 number, it could be infinity, it could be 0. Who knows? The point is that when people try to account for the one-loop expansion of these modes, they treated this integral as if it was an order 1 number. And as we shall see, and probably as you're already have some intuition from the previous lecture, that is slightly incorrect. Okay. So what happens? How do we do the calculation using this method? Again, well, what we saw previously is that it was important to go slightly away from extremality. So away from extremality. I have another metric perturbation, which is just a classical metric perturbation. But I can still consider this classical on top of this classical metric perturbation. This is the perturbation that takes my black hole from being extremal to near extremal. On top of these metric perturbation, I consider quantum fluctuations of the metric, and the same for all other fields. So A still goes to A plus A tilde, psi still goes to psi plus C tilde. Okay, what happens once I introduce this classical background, slightly different classical background? Well, what happens is not much happens for the modes that weren't zero modes. So if I consider the differential of my differential operator d prime, so this is the differential operator that's associated to the background g plus delta g, and I consider it for a scalar, the eigenfunctions for the scalar and eigenvalues remain somewhat unmodified. Namely, previously they went like 1 over S naught, they went like 1 over 2 squared, and they still go like 1 over S naught, plus things that are small in the temperature, linear in the temperature. So it's not affected much. However, the zero modes, so for instance, if I take the mode that I wrote previously, that ugly mode, HMN, and compute its action, the action of this new differential operator to find the new eigenvalues, what you find that modes that were previously zero modes now get a mass. So zero modes get a mass. And their mass, if you literally plug them into the action, turns out to be proportional to T over MSL2. So this is perfectly consistent with the identification of these modes epsilon as the Schwarzian modes that we discussed in the morning lectures. Those modes also had a mass when the temperature was non-zero, which was given by this coupling. Sorry, this is the so this is HN. Great. And specifically, for instance, if I look at these modes that correspond to boundary state fluctuations, and I explicitly evaluate the quadratic piece of the action in the presence of this classical background, you now get that I quadratic is T over M breakdown times the sum over all modes, 2 pi squared, n squared times n squared minus 1, epsilon n squared. This is precisely the quadratic expansion we found this morning for the Schwarzian theory at second order around the saddle. So same as Martin. And we know now what happens when we integrate it, when we integrate this mode out. It gets, the one loop correction becomes very large as the temperature becomes to zero, goes to zero, and specifically, the partition function now becomes, so there's q to some power. This C log, I promised that I would write it, but I forgot. Sorry, 1 second. Yeah, it was equal to -1 over 180 times 964 plus number of scalars plus 62 times the number of vectors plus 11 times the number of fermions. So here we see that this logarithmic correction in the charge depends on the exact field content of the theory. So it's not quite universal. It only depends. It's universal in the sense that it depends on the number of free fields of each different species. But in addition to that, integrating out over zero mode, we get this additional factor of t over m breakdown to the power 3/2. And then finally, we get e to the s naught minus beta m0 plus 2 pi squared t over m breakdown. So when t is very tiny, this correction can actually dominate over the standard logarithmic and area corrections that people discovered for black holes in the past. And in particular, something even, so what that means is that in the limit when the temperature goes to zero, this path integral, regularized, formally gives a zero answer. So, even though people correctly computed the coefficient of this power of q, the power of q that appears in the logarithmic corrections of the area, that affects the logarithmic corrections of the area, they missed the fact that the constant multiplying it in the one loop determinant can only actually be regularized to zero.
In the logarithmic correction calculations, those have been checked, for instance, again, string theory or...
Right. So the checks against string theory are only in supersymmetric cases. And as we shall see, you see the number of zero modes, as you asked me, highly depends on, the set of large diffeomorphisms or super diffeomorphism if you work in supergravity. And it turns out that in supergravity, you have an additional integral over fermionic modes. And that additional integral causes the result to become finite at extremality. Good. So,
Luca,
yeah.
can you repeat the comment about the regularization of that?
Yeah, so here what we've done, right, when we integrate out these modes, is that we zeta function regularize the one loop determinant. It's an infinite product over factors that depend on the temperature. So to make sense of it, one would have to consider the ratio of two partition functions. But in particular, if I consider the ratio of a partition function evaluated at t equals 0 and the partition function evaluated at some non-zero t, you will find that that ratio goes to 0. So z of t equals 0 and z of some small t, such that black hole is near extremely, this goes to 0, meaning that this integral goes to 0 when considered in the ratio between partition functions. So, while this answer was correct. It's correctly accounted for log area, log Q, log in Q or log in area terms in the free energy. It missed this important factor that becomes the crucial piece, the dominant piece at extremality. One more comment is that actually you might expect that this means that the ratio of that what was correctly computed is the ratio of partition functions at different as you know one takes the limit of zero temperature. So is this what is this? Z of Q1 as T goes to 0 divided by Z of Q2 as T goes to 0, evaluated at the same temperature. Naively, you would say that this is Q1 divided by Q2 to the power C log. But that's a bit incorrect because in addition to that, this breaking scale also depends on the charge Q, which means that secretly this regularization introduces dependence on the charge of the black hole. So the correct answer here is that it's Q1 over Q2 to the power C log times and breakdown is Q cubed is proportional to 1 over Q cubed. So times Q2 cubed divided by Q1 cubed to the power 3/2 times e to the pi Q1 squared minus pi Q2 squared. So even the ratio of partition functions, even for the ratio of partition functions, you have to be careful of the regularization of these modes. Even though you might naively think that these path integrals, are charge independent.
So in the supersymmetric case.
Yeah, I will get to the supersymmetric case in the second part of this lecture. Right. But maybe you have a quick question.
Question for that.
Okay. So finally, before we take a break, I want to give a third derivation. Same result.
Sorry.
Yeah. Any questions?
Yeah. In the first derivation, you dropped out the zero modes in the Schwarzian.
Yeah, so the meaning of zero modes is slightly different there.
Yeah.
Those are zero modes that we actually have a reason not to integrate over because the geometries are identical.
Mm-hmm.
They are just isometries of the space-time. Here, in fact, we saw that the large diffeomorphism wanted to, in some sense, include the isometries, but we excluded them precisely because, you can't generate a large diffeomorphism by an isometry. But we do have at exactly zero temperature, all the modes of the Schwarzian become zero modes. So it's different than the SL2R zero modes that we discussed previously. The zero modes are only appearing once we take T to be exactly 0. It's coming from the fact that if I said T equals 0, of course, the weight of epsilon n is 0. So, I should integrate over these modes fully. Does that answer your question?
Yes. But I mean, the three halves now, where does it come from?
It's exactly the same origin. It comes from the fact that we only are considering these modes, these zero modes are only labeled by n that is greater or equal than 2. That's because the n equal 1, 0, and n equal -1 corresponded to an SL2R isometry that did not generate large diffeomorphism.
Okay.
That affected the boundary. Okay. So derivation 3. Any other questions before I go into this?
If I can keep bothering you, the fact, so here you're regularizing the zero modes by turning on temperature. But if I remember, the heat kernel method at zero temperature can also account for zero modes, right? There's some contribution. Usually people write in terms of -1, blah blah blah.
Yeah. So that's correct. That's actually part of the C log. I swept that a little bit under the rug.
I see.
But there's still an integral that you have to do. That's an integral over some fields that are seemingly dimensionless. They're seemingly independent of the charge of the black hole. That d epsilon, dA, and dAn that I wrote previously are independent of Q. They should just give an order 1 number. It just turns out that they give 0
But
when I take T going to
the
0.
C log up there takes into account it has this zero mode contribution to the heat kernel for the Q dependence. Like
Sorry, can you repeat the question one more time?
the C log that you compute this using heat kernel.
Yes.
There you have to be careful about.
You have to be careful
and
about.
You've already taken this into account. In
Yes.
the final result.
Yes.
Thank you.
Okay, so derivation 3. Some of you might be sticklers and want to make sure that don't even believe what's even a gravitational path integral. What is Luca talking about? So for this reason, it would be nice to give a boundary derivation in the context of IPFT. Can we derive these results from the CFT? The density of states that I saw earlier should just be the density of primaries, or the density of operators of scaling dimensions that I have in a fixed charge or a fixed angular momentum sector above the lowest energetic state. So in principle, if I knew the spectrum of the CFT, I should be able to reproduce the plot that I showed you earlier. For rho of E, it will be rho of delta, where delta is the scaling dimension. So unfortunately, there's no proof of this derivation for arbitrary number of space-time dimensions, but what we can do is prove it in 2 dimensions, namely in ADS3, CFT2, without ever relying on any bulk ingredient. So let's imagine that I consider the partition function of a 2D CFT that has a left moving temperature and the right moving temperature. These are the inverse temperatures. Good. And I start by performing a modular transform. So 2D CFTs are modular invariant. So I can relate this partition function to the partition function evaluated at 2 different temperatures, namely these 2 temperatures. And now I can simply expand this partition function in terms of these objects called characters, Virasoro characters. So a partition function is a sum over Virasoro characters, starting with the character of the identity operator, or the vacuum Virasoro character, evaluated at, sorry, this is 2 pi I. My bad, sorry for the typo. 2 pi I over beta left, pi identity, 2 pi I over beta right. And then in addition to the vacuum Virasoro characters, I have Virasoro characters for all the Virasoro primaries. This proof, by the way, is very similar to Cardy's proof for the growth of states, and I'll make a comment about that. So this equality holds for any 2D CFT that's modular invariant. Actually, given the time, perhaps we can take a 10-minute break. Okay. Any questions before we take the break, though? Okay, great.
You're online.
Great.
Let's see.
I'm just gonna write two formulas before people come in. For the vacuum Virasoro vacuum Virasoro character and the primary Virasoro character. Here, eta is the Dedekind eta. And tau is related to q by q equal to e to the 2 pi tau. Maybe should I wait 30 seconds for people to come back in? Okay.
Somebody can go and clap.
I clapped.
You are interactive enough.
More clapping. Okay.
The cigarettes are. Oh,
I'm the only one.
you're the only one. The other ones really don't have an excuse.
Yeah, that's true. The French one, the French people are.
Alright, sorry, online people, for the small delay.
Oh, the only two that are missing are Eric and Gabriele.
Yeah, they are talking.
Okay, no worries. Okay, then I'll continue. Eric already knows this derivation by heart, and it's 2D CFT related, so, I'm sure he can do without. So, good. So, this is a formula that holds in any 2D CFT, where these are the formulas for the vacuum Virasoro primary, the vacuum Virasoro character, and primary Virasoro character. So now let's analyze what would happen in a holographic CFT. So this is a CFT that has large central charge. When we look at the limit in which what dominates this partition function are rotating BTZ black holes that are close to being extremal. If they're close to being extremal, then it means that we need to set one of the temperatures to be very small. Namely, we will set the inverse left temperature to be of order C. And if I want my black hole to dominate over the ADS-free vacuum, so I want my black hole to be above the Hawking-Tate transition, then it turns out that I need the following relation between beta left and beta right. And what one finds in this limit is that chi, if you stare at these two formulas, you'll find that the product of these two characters, actually dominates in the entire partition function. Great. The reason why it dominates is, let's consider the ratio between, this is an H bar. Let's consider the ratio between chi of H bar and up to pi I over beta right, and chi of the identity of 2 pi over beta right. So this is just plugging in the specific value of q and taking the limit when beta right is very, very tiny. In that limit, this goes like an exponential of minus 2 pi squared divided by beta right times h bar. And because I'm taking beta left of order C and beta left times beta right to be some order 1 number that's smaller than 2 pi squared, what you get here is that this goes like e to the minus 2 pi squared times c times h bar. Now, in holographic CFTs, we expect that there is a twist gap, which means that the first primary starts at some non-zero value, which we can call h bar gap. And by setting h bar gap to be different than 0, we find that the contribution of vacuum Virasoro primaries, the Virasoro primary characters to this sum is much as exponentially suppressed in the central charge compared to the contribution of the identity operators. So now the only thing that this means, well, this means that we just have to evaluate what these characters are in this limit, and we'll find the dominant piece of the partition function. So this is a very easy exercise. You look at these two functions that have very explicit formulas. And then the limit that's written on the upper right corner, pi 1, I have the identity of 2 pi I over beta left is equal to 2 pi over beta left to the 3 halves times an exponential of beta left over 24 plus c over 24, 2 pi squared over beta left. And chi 1, 2 pi over beta right is just equal to e of c over 24, 2 pi squared over beta right. This might already look familiar. Things look even better if I change basis and talk about the partition function of a black hole that has fixed angular momentum. So for that, I have to actually define the physical temperature, which is equal to half beta left plus beta right, and theta, which is essentially like the chemical potential for the angular velocity. The chemical potential for the angular momentum. In other words, theta is related to the angular velocity. The partition function in a fixed spin sector can be obtained by performing a Fourier transform with respect to this theta, right? Since theta is like a chemical potential, the partition function of fixed periodic sector is like d theta e to the minus I theta j d of d theta. And here, I'm performing things in order to recover the limit that's written over there in terms of beta and j. It turns out that I have to consider still central charge much bigger than 1. That didn't change. Beta is of order c, and j much larger than the central charge. So this is a very extremal, very nearly extremal BTZ, rotating BTZ black hole. So performing this Fourier transform on the product of these two Virasoro vacuum Virasoro characters, one finds that the partition function in fixed beta, fixed j sector can be written as e to the s naught times integral over dE sinh of 2 pi square root of e minus e naught over m break times e to the minus beta e minus e naught. So So here the integral starts from E naught to infinity, and let me write what S naught, E naught, and M break are in this situation. M break turns out to be 24 over C. So it's a very tiny energy scale in ADS per units. That is the completely analogous to the thermodynamic breakdown scale that we saw in higher dimensional near extremal black holes. E naught is J minus 12, J minus 112. This is just the extremal mass that BTZ black hole, rotating BTZ black holes take. And S naught is 2 pi square root of Cj over 6. This literally just comes by taking this formula, doing the following replacement, taking the Fourier transform, and then writing the partition function in a way that makes the density of states obvious.
Sorry, I don't understand why the left sector character is different from the right sector.
Oh, because they're different limits. Beta left, right? It's their exactly opposite limits. Beta left is very large.
And the other
And
is
beta right is very small. And the vacuum Virasoro character has these two different properties in these two limits.
In the ratio between delta H and delta 1, what is the final result has a plus or minus in the exponent? In the final.
Here?
We have the ratio between the characters for H bar. Yeah.
Ah, sorry, this is a minus. So it's minus some number. This number is set by exactly what I set beta right to be. But I set beta right to be of order C inverse, right? That the beta left is of order C. So it's some number such that this product is smaller than 2 pi squared. But the important thing is that if H bar starts at H bar gap, then the contribution of all these Virasoro primaries is arbitrarily suppressed.
And just the sign is like it's an arbitrary log suppression rather than.
Yes. Does anyone have a USB-C charger? I didn't realize my battery would run out.
I can rush and that's.
Thank you. Okay. So, yes. It scaled linearly with M Planck. It was M Planck over Q cubed.
And here it's 1 over.
Yeah, here it's easier to think about it in terms of the central charge, I guess. It's in units of energy. So here you can think that there is, in addition to L Planck, there is the ADS free radius. So it appears through the ratio between L Planck and the ADS free radius, right?
Sorry, can you say again why the product of beta R are less than 2 pi squared?
That's because this, I think, is the limit in which black holes, these rotating black holes, dominate in Z. If they don't dominate, then okay, I'm just studying the contribution of the vacuum, so that's not an interesting limit. Good.
Sorry, it's kind of hidden under the curve, but J is what?
J is much larger than the central charge. So J is an arbitrary, but order central charge, but the ratio between J and C is arbitrarily large. Yeah, so J is just some fixed number. Good.
So this is the limit.
It's not the Cardi limit. It's a refinement of the Cardi limit. The Cardi limit cannot be applied when you scale beta left to be of order C. Cardi applied his argument when beta left times beta right was smaller than 2 pi squared, but he took beta left large, but not of order C. When you get beta left of order C, what happens is that this vacuum Virasoro character contains this one loop piece, which becomes very important. So Cardy only saw that the density of states grows exponentially, right? So it went like e to the square root of e minus e naught over m break type some number. This is what Cardy saw. But that's precisely because in the limit that he considered, it was okay to ignore this one loop determinant. So, by the way, this also implies that actually well, we'll talk about this in the supersymmetric case, but technically the derivation of Strominger and Baffa is slightly wrong because they use the Cardy limit in a limit where beta left is sent to infinity because they want to capture the contribution of extremal.
It's the bus time. Some buses.
Okay, not a problem. Okay.
So the extremal is when one of the betas is infinite.
Yeah, it's when one of the betas is very large. Here we're studying near extremal. When we would send beta left to infinity, we would study the exact extremal limit. Good. And yeah, let's see. Where is the? So the point is that all these results now derived from the 2T-CFT side confirm the previous gravitational results.
Strominger Baffa would be the limit beta goes to 0, right? Not beta goes to C.
No, it would be beta left goes to infinity because they want the
beta is the temperature.
Beta is the inverse temperature.
It is the inverse temperature. That's going. Or it's sorry.
The T-right is going
Sorry,
to 0 till
I meant whatever. 0 temperature, not
Yes,
temperature of order.
exactly. Yeah, good. So we'll talk about what happens for supersymmetric black holes in a second. Why does actually, you could have concluded from this computation that, okay, maybe extremal, maybe even supersymmetric black holes don't have a degeneracy, right? This proof is very general, right? It only assumes two things. It only assumes that I have a CFT that is modular invariant, so that's automatic, that has large central charge and non-zero h-bar gap. Why does it not apply to supersymmetric theories? It's because from the perspective of regular Virasoro characters, in supersymmetric theories, there are states that have h-bar gap equal to 0. And those are the characters of the supercurrent. It's the regular Virasoro character of the supercurrent. The idea is that that character combines with the vacuum character in a more complicated character called the super Virasoro vacuum character. So these formulas have to be changed in the supersymmetric case because the assumption h-bar gap greater than 0 is incorrect in a supersymmetric theory. But still, one has, even in a supersymmetric theory, one has to consider these limits very carefully. So this brings me to a point that I was asked many times so far. Oh, perhaps I should mention that an open question for all this analysis is what should we do to prove that this is the density of states of operators in a higher dimensional CFT. We don't have this very powerful tool of modular invariance at our disposal, but perhaps someone could find a trick, maybe from some crossing equations or something of that sort, to actually prove that the density of states, the density of like near extremal microstates, also has this behavior in higher dimensional CFTs. So next, we want to ask, what about black holes in supergravity? How is this all consistent with the count of Strominger and Baffa? That seemingly tells us, confirms that the extremal entropy is proportional to area, the area at extremality over 4g Newton. While all our calculations claim that this extremal entropy receives extremely large corrections. So how could it be? Where does our computation fail? So we should redo the computation for black holes that are nearly supersymmetric. And I won't go through the entire computation. I'll just schematically tell you what how the computation goes and what the results are. Nearly supersymmetric, I mean that we're going to expand around extremal black hole geometries that have a killing spinner on them. We saw that in so far, an important feature was played by the isometry group of the near horizon region. The power of beta to the 3 halves was related to the number of bosonic generators of SL2R. So you could ask, do supersymmetric black holes have a bigger isometry group in their near horizon region? Perhaps that causes, intuitively, the power of beta to change. And that's indeed the case. The near horizon isometry group for supersymmetric black holes is different. So, for instance, if I talk about black holes in 3D, in n equal 1 comma 1 supergravity, in ADS-free, these black holes turn out to have an effective description in terms of n equal 1 JT gravity, which is a supersymmetric, supersymmetrized version of the effective field theory that we talked about earlier. And the near horizon isometry group is OSP 1/2. So this has SL2R as a subgroup. The maximal bosonic subgroup is SL2R times some discrete groups. If I talk about n equal to 2 comma 2 supergravity in ADS-free, or any supersymmetric black hole in ADS with d greater than 3, then these black holes are described by different versions of n equal 2 JT gravity. And the near horizon region isometry group is SU1, 1/1, which is a supergroup that has SL2R times U1 as a subgroup. So there's an additional U1 isometry, which is related to SL2R by some fermionic symmetries. And finally, if I talk about n equal 4 comma 4 supergravity in ADS-free, this, by the way, is the type of effective field theory in ADS-free that's relevant for the black holes discussed by Strominger and Baffa. Or I talk about black holes in supergravity in n greater or equal than 2 supergravity in flat space. Then this is described, guess what, by a version n equal 4 version of JT gravity. And this one has an SU1, 1, flat 2 isometry group, which has SL2R times SU2 as a subgroup.
Does it make a difference if you get ADS3 times S3 times T4 or K3? If you do K3 instead of a T4, you get less supersymmetry.
But I think so if you discuss, so you get ADS-free times S-free times T4 versus K-free. I think I thought they're both 4 comma 4 in ADS-free. Maybe one is 4 comma something else.
I don't know.
I don't remember.
If you did ADS 3 times S3 times T4 versus K3,
Makes no difference.
makes no difference. So the ADS 3 theory is the same.
Sorry?
0, 2, 0.
Yeah, so if we discuss 0,2 or 0,4, it just depends whether or not your black hole is supersymmetric with respect to the 2 or 4, but the result is still universal.
Oh, so if you look at the 4 charge block, if you look at an ADS 3 times S3 mod Z.
Yeah, I think the only difference is that the isometry group here is slightly larger if you consider 4, 4. I think it's SU1, 1/2 times SU2. But there's no SU2 if you consider 4, 0, I think. But that doesn't make a difference because that SU2 commutes with all fermionic generators of the isometry. Anyway, so to redo derivation 1, one in principle looks at the dimensional reduction of this near horizon, of this theory of the near horizon region of a supersymmetric black hole. Let's say if we are interested in black holes in supergravity and flat space, you redo the dimensional reduction, and instead of JT, you get n equal 4 super JT. Once again, it turns out that the integral over the dilaton, but this time also over the dilatino. The dilaton has a super partner called the dilatino, not a big surprise. That just sets the bulk action to be completely vanishing. And you're just left with a boundary term, just like before. Just like the Schwarzian was the boundary term for JT. In this case, it turns out that there will be an n equal 4 version of the super Schwarzian. And this n equal 4 version of the super Schwarzian contains, so the action is, again, has a coupling, which is given by this breakdown scale inverse. This is still exactly the same breakdown scale as before. Here you can consider black holes that carry a single charge. This breakdown scale would still be go like 1 over q cubed. But now, in addition to the Schwarzian, tau, you have an additional mode that parametrizes fluctuations of rotations. This is this mode that corresponds to this SU2 isometry, whose action is that of a particle moving on a group manifold, on an SU2 group manifold. It's this. And in addition to this, you have fermionic degrees of freedom that couple to both T and G in complicated ways. This action is really bad, really complicated. But an abstract way of describing it is T, as we said before, T of tau. We can think about it as the space of functions living on dFS1 over SL2R. This is our integration space for T of tau. G, I said it's like a particle moving on an SU2 group manifold. So we can think about it as living in the space loop SU2 over SU2. Loop SU2, just in case you haven't encountered it, is the space of functions that are maps from SU2 to a circle. Sorry, maps from a circle to SU2. So it's a space of functions, and here we quotient by SU2 because just like before, when we quotiented by isometries of our near horizon region, here this SU2 is the isometry in the case of 4D black holes in flat space is the isometry of S2 on such black holes. But if I want to write everything in a formulation that's more manifestly supersymmetric, I can talk about the space of T, G, and fermionic fluctuations together. And this parameterizes functions living on d/4 divided by PSU 1,1/2. So dFS1/4 is like diffeomorphism on a circle superspace. Anyway, this is just a technical detail. And it turns out that once again, the partition function of these black holes is one loop exact. This mode, so let me just review before I talk about the partition function. Let me just review from the perspective of the second derivation what everything corresponds to. The first, the T still corresponds to fluctuations of the boundary shape. The G parameterizes fluctuations of rotations of the sphere as I move around the boundary circle. And psi parameterizes fluctuations at the boundary of the gravitational as I move around the ADS2 boundary. And together, they form this space. So again, one can either proceed by writing down this full action or by just perturbing the extremal background, the extremal background to quadratic order, and understanding what happens at quadratic order to all these large super diffeomorphisms. And one obtains the following partition function that has a function of two parameters, beta and alpha. Alpha will be beta, well, yeah, let me write it as beta and omega. Omega is like the angular velocity that I fix for the black hole, which it turns out to be related to the chemical potential that you can impose for this G. So in terms of beta and alpha, the partition function can be written as e to the s naught minus beta m naught. This part remains completely unchanged. But now we have an infinite sum. This infinite sum comes from the fact that this part of the action involving G has an infinite number of saddle points. So there's a sum over n, infinite number of saddles of G of tau of beta over beta times m breakdown times 2 cotangent of omega times beta divided by 4. Divided by 1 minus 4 m plus omega times beta divided by 4 pi squared times omega times beta divided by 4 pi plus n e to the 2 pi squared m breakdown inverse times t times 1 minus 4n plus omega times beta divided by 4 pi, everything squared. Okay, so let's unpack this a little bit. So here I put together the result from all one-loop determinants, both from the Schwarzschild mode, the mode, this SU2 fluctuation, and from the fermionic fluctuations. But before that, let's look at the classical action. So this first term, the 1 multiplied by this factor, is precisely the classical action that we found for the Schwarzschild itself. for the bosonic part of the Schwarzian. And that just comes because this theory has the same saddle point for the Schwarzian as before. So this comes as on-shell evaluation of the Schwarzian. This piece comes from the fact that this G, as I said, has multiple saddles, that it just comes from evaluating the on-shell action on each one of these saddles, and that's why this thing in the exponent depends on n. So this is the on-shell evaluation of the particle on SU2. Sorry, on SU2. Sorry for the tiny writing over there. Okay. Actually, before I go, let's discuss something else. Let's look at the power of beta. Previously, the power of beta came from the number of bosonic generators alone. So that was in the Schwarzian, that was 1 over beta to the free half, because there were free bosonic generators in SL2R. But now we also are integrating over this loop SU2 over SU2 modes. And that provides another factor of beta, which also goes like 1 over beta to the free half. They're also bosonic zero modes. So this is SL2R isometry. This is SU2 isometry. And finally, in addition to that, I have beta, this time to a positive power, that comes from the number of fermionic generators of my isometry group. PSU1, 1/2. If you look at the algebra, you'll see that it has 8 distinct fermionic generators. So I have a beta to the power 8 divided by 2, which in total gives me 4 minus 3 beta. So this is where this power of beta comes from, and all the other n-dependent pieces come from evaluating either the one-loop determinant of this particle moving on SU2 or the fermionic degrees of freedom that couple to this G and are thus affected by the specific saddle on which I evaluate the one-loop determinant. So this is a really nasty expression, but it turns out that this infinite sum has a very nice Laplace transform. So the Laplace transform of this sum is the density of state, just as before. Any questions before I talk about the density of state? Okay. So if I look at the density of states above extremality, so here E is m minus m extremal. It turns out that first of all, I get an exact delta function at extremality. So this, naively, you can see it's a consequence of the fact that when I take beta going to infinity, pieces of the sum are growing. So previously, when I was taking beta to infinity, the partition function was going like 1 over beta to the free halves. And that's why the density of states was going to 0 as the energy was going towards extremality. Now, each term is blowing up, but the sum over all terms turns out to give something finite, and it gives e to the s naught with coefficient 1. It turns out that all the results, if I take Laplace transform both with respect to beta and a Fourier transform with respect to omega, to extract what the what the density of states in a fixed J sector is, it turns out that I see that the states arrange themselves into supermultiplets in the following way. The density of states, this delta function only contains states that have J equals 0. Then at exactly the scale M breakdown, I have support both for states that have J equals 0 and half.
So this is a function of energy, or
Oh,
this is a function of?
yeah, it's a function. It's as a function of energy above extremality. So here is 0. Is just the extremal energy. So it's E is M minus M0.
Question, you also have normally you have entropy when you have states which have J, like for example when you have black rings. So those have entropy, and they have J equals to finite.
Right.
And they have energy, they have entropy at extremality. So
That's right. That's right. This is just coming from a perturbative expansion around a single saddle point.
oh, it's a single saddle. Okay.
So in principle,
you're looking at the black hole. Okay.
Exactly. So this is just the 1 over G Newton expansion coming from the 1 over G Newton expansion around the simplest supergravity solution, which is just the Reitzer-Nordstrom supersymmetric version of Reitzer-Nordstrom. Okay. Then at 4M breakdown, I have another multiplet that contributes that has J equals 0, half, and 1. And so on and so forth. As I go higher and higher in energy, there are multiplets that contains black holes with higher and higher pairs of spins. Next, it's like 1, 3 halves, 2.
So the 1 half is where? I mean, so the 1 half, if I think about the black hole having an SU to right and left. Sorry. So
these are 4D black holes.
4D black holes, okay.
So these are just the fermionic states.
Okay, so those are not momentum excitation. They're just rotation, the 4D rotation.
They're 4D rotations.
And what's the index? So the 1 half is the spin in 4D, and the 1 is
spin 1. So there's a multiplet, a black hole multiplet of states that has J equals 0 and half. And there's another multiplet that has J equals 0, half, and 1. There's another multiplet that has J equals half, 1, and 3 halves, and they all start at higher and higher energies.
so multiply vector.
Yeah, like and the idea is that this is the BPS multiplet, and these multiplets are long. There's a long multiplet that only has these 2 spins. And there's other long multiplets that can have arbitrary spins, but they contain free spins. That's what you get from the representation theory. So for instance, if you only want to look at states that have angular momentum 0, these are like scalar black holes. They don't rotate. You would sum the contribution of these 3 multiplets. These are the only multiplets containing states with J equals 0. And you'd get a delta function . You'd get a delta function at extremality and a continuum of states that has that starts at a breakdown and like this, and has a small discontinuity when this other supermultiplet kicks in. A small discontinuity in the first derivative. That's because we're summing 2 functions, both that stars that have support at different values.
So you break down in the only 5 language, for example, this is 1 over N1 and 5, I guess.
Yes.
I'm sure the second one is at 4 and not at 2.
I thought it's at 4, but
it's at 4, okay. Because so there's some calculations which we did a while ago about microstate geometries, which are actually some supersymmetric ones, and then on top of each of them you can build some tower of states which have J equals to 0, 1, so 1 half, and then you can build another tower. But the gaps, and so the point is you have some supersymmetric states, and then you can put some perturbations on top, and then you can build first harmonic, second harmonic, third harmonic, and so on. So in one with some values of the J, and then and then you have another tower which has some other value, and so the towers. So we see these towers, but I think that the second one, I think.
I should double check. I can look at the paper again.
Yeah, careless. That's all we know.
But this, in any case, should be compared again to the semi-classical result. The semi-classical result doesn't change whether I consider Reinstein-Nordstrom or supersymmetric Reinstein-Nordstrom. Their on-shell actions are the same. So the semi-classical result looks like this. So it asymptotes to the correct density of states at large energies above extremality. But once I start reaching energies of the order of this breakdown scale, I see that like the spectrum now looks completely different. So in particular, I should make two comments about these black holes. Number one, they have a large degeneracy that you can see from the gravitational path integral. So this is consistent with the count of Strominger and Vafa, and it's also explained by the fact that there's supersymmetry that protects BPS states. So this is consistent with the puzzle 2 that we posed in the first day. And also at precisely the breakdown in between the extremal energy and the breakdown scale, I find that there is a gap. And this gap is precisely the one that was predicted by Maldacena and Susskind in the 90s using an argument that weak coupling. Coincidentally, you can actually prove that that's the exact value at which the spectrum starts in the gravitational theory. I don't think that should mean that that calculation is trustworthy because it's a calculation in weak coupling. Nevertheless, perhaps dimensional analysis got lucky and they predicted the right gap scale.
You can also do it in supergravity. So the point is, we have all the microstate geometries which are dual to states, which are basically in the j equals to 0 and supersymmetric. And then if you look at waves on top of them, you see exactly the 2 over n-5 gap, which you expect from the CFT. So in supergravity, you also have a confirmation that you have exactly this tower on top of so you have the supersymmetric microstate geometries which are dual to some states of the dual CFT. And then if you put waves on top of them, you see exactly this gap coming from from the ground state, which is supersymmetric. The first excitation, you have exactly the 2 over n-5 times Ry.
I see.
So you can also check a strong coupling in.
I see, but those states don't reproduce this density of states, right?
Well, we don't know yet, actually.
You don't know.
Yeah. I mean, you have a huge amount of states at 0 energy, and you can just build a tower on top of all of them.
Right.
But then there are questions about mixing but there's.
Yeah.
So that's you also see that there won't be any cancellation in trace of -1 to the f, right?
That was comment number 3. So comment number 2 is that this gap and the fact that the spectrum looks very different at small temperatures addresses puzzle number 1. Comment number 3 is that we find that all the states that exist at extremality have j equals 0. The way to see that from this partition function is that you can take the limit when omega goes to 0 and take beta going to infinity and compute this sum in that limit, or you can take omega beta over, or you can take omega beta over 4 pi to be equal to half. That's precisely the type of computation that I described in the first day that's supposed to compute an index. You find that the answer is temperature independent, and you find that it completely agrees with the answer that you get when you take omega equals 0 and beta going to infinity. And this is a different way to confirm that all the states that populate the ground state are bosonic.
So in your figure here, when you say going to 0, this is on some scale where sort of the vertical scale is like in units of central charge. Right? So in other words, if I had a density of states which was going where the entropy was some smaller power of the so the kind of thing that happens in microstate geometry is you don't get something that grows like q to the 3/2 like the Sturm-Liouville entropy. You get something that grows like a lower power respective of charges.
Mm-hmm.
So the question I'm asking is, on the scale of your graph here, would that, if it had some entropy which is growing less strongly than the Sturm-Liouville entropy, would that show up in your plot as quote unquote going to zero as you approach the bound?
In particular, I mean, what Emil is asking, you can build supersymmetric solutions. That's the topic ADC on this.
So all the ones that are known in microstate geometries are things which have non-zero angular momentum.
Actually, the Gibbon sorting ones have zero, but the superstrata, all the ones whose CFT dual is known, they have non-zero angular momentum. There's a huge amount of them. And in the dual CFT, you can also do the same.
So it's a macroscopic number of states, but entropy growing with a power smaller than square root of n1, n5.
So, but they are close to their extreme.
They're all supersymmetric.
They're all supersymmetric.
They're all extreme.
But presumably in long multiples, like what you're showing.
But then these are not supersymmetric.
The ones, no. So there are two questions.
The question. So, like, would you see in a supergravity solution that it was quote unquote not supersymmetric, or would you see that there's some nice solution which looks like it has a Killing spinner, but it just because it has non-zero angular momentum in your plot, it has to be long.
All these states that are in long multiplets, if I act with a supercharge on them, I get a non-zero answer. So I would say that all these states are non-supersymmetric. So I'm not sure that I could say that these geometries have.
I go exactly to what looks like zero. Okay.
Yeah.
Is that really zero? What I'm asking is zero, or is it just e to the entropy where the entropy is growing less strongly than square root of n1 n5?
Yeah, I understand what you're saying. It should be taken as e to the entropy where entropy grows less than n1 n5. Yeah, because
it's living on the BPS bound.
Yeah, so just as before, here we're considering only a perturbative expansion in 1 over g Newton around this supergravity solution. So that means that if you have other solutions that contribute by a non-perturbative amount, so they're non-perturbatively suppressed in e to the 1 over g Newton, you wouldn't see them in this perturbative expansion.
Black rings. I think what Emil is asking is it's a different question. So in the dual CFT, we know that we have all these states which have a non-trivial J.
Yes.
We can put J equals to 1/2. We can put some formula 0 states.
Yes, but we don't know where they come from in gravity, right? They come from your superstrata solutions, I imagine. But what I'm saying is that you can't see them in perturbation theory around the black hole solution. That's it.
That's true.
The black hole is only capturing J equals to 0 sharp. You're saying that the black hole
for in terms of BPS states. And probably if you look on the CFT side, I do think that actually from the CFT side you cannot tell, because from the CFT side you can only reliably compute an index. So you can't actually tell that a strong coupling all the states are bosonic, or whether they're bosonic at leading order and have non-perturbative corrections in 1 over g Newton.
We don't know of any gravitational cell that counts the number of superstrata.
But the stupid question.
Okay.
Stupid question. So if I have some fermion zero modes on top of some solution, so in the D1E5 system, for example. Sorry. The other question. If J equals to 0, there's a difference between J equals to 0 and having an isometry with respect to the transverse group. So you can have, for example, a figure 8. A figure 8 solution, it has J equals to 0 because there's some circle moving like that. So there's a J plus and J minus which cancel. So the figure 8 breaks the rotational isometry. Can we figure out whether the states you have a J equals to 0 in the delta function there, can we figure out whether they preserve the transverse rotational group or not? Or they just have J equals to 0? So there's a question again, you can have J equals to 0, but
so the way in which one obtained this J equal to 0 is somewhat not trivial, right? Because the way in which we did the computation to begin with was that we fixed the angular velocity, and that changed our boundary conditions for these large super diffeomorphisms. And then we did Fourier transform in terms of omega to recover what the density of states and partition function at fixed j is. So I would say that these j equal to 0 states should not necessarily be thought of as some classical geometries, because they come from, geometries that are highly fluctuating.
Not if they're rotation invariant or not, that's the question. So for example, if you look at...
I think that they are rotation invariant in the sense.
But again, you can have j equals to 0 things which are not rotation invariant. Again, a figure 8 has j equals to 0, but it's not rotation invariant. If you just put some, some flying a figure 8, it has angular momentum is 0. You just have some object going like this, so there's a positive contribution.
Okay, maybe I should be even more specific. Here we chose an axis, which we call the z-axis, and we measure the angular momentum with respect to that z-axis.
Sure.
So
you can have zero angular momentum, and you can have an object which is looking like a figure 8, so which breaks the isometry corresponding to rotations around the z-axis. So again, you can rotate around the z-axis, and then you have angular momentum and break the isometry. But you can also have a figure 8 rotation, which breaks the isometry, but still has j equals to 0.
I understand what you're saying. I don't completely know the answer for that. Maybe a good analogy would be, hydrogen atom has states that have j equal to 0. Those are spherically symmetric, right? The way in which I think we know that is because their wave functions, when we compute them, we can check that they're spherically symmetric. And
the D-1D5 system, for example, many states which are spherical, which have j equals to 0, which look like some figure 8 Lunin-Matur geometry or Lunin-Matur geometry, which are not, so they're breaking the SO4 transverse symmetry, but they have j equals to 0.
Good. Okay, I think I know how to answer your question, and I think the answer is that the states here do all have j equal to 0 again at the leading non-perturbative order. The way to see that is if you take the partition function, this partition function, you can take the second derivative with respect to omega. A second derivative with respect to an angular velocity pulls down a factor of angular momentum squared. And I would have said, and this computes in the figure 8, while it's true that, if you take a figure, let's say you have a wave function that has peaked around the figure 8, it's true that might have on average jz equals 0, but I'm not sure that it would have on average j squared
It cannot be 0, indeed.
Yeah, so that's how I would probe that question. Yes, I think so. And I think one finds that all these states have j equals 0. But again, as Emil asked, this is a statement about the degeneracy of states at leading non-perturbative order in 1 over g Newton. So what might possibly be happening is that you have other solutions, I don't know, figure 8 solutions, crazy solutions.
The reason is the following. In the D-1D5 CFT, if you look at the states which give it the Stromer-Javafa entropy, there are 4 bosonic modes and there are 4 fermionic modes. To get a 6 over 6 and 1 in 5p in order to get the Stromer-Javafa entropy. You get 6 coming from 4 bosonic degrees of freedom, 4 fermionic ones which contribute to 1/2. Now, 2 of the fermionic ones break the SO4 spherical symmetry. So if you look at the generic Stromer-Javafa states, which have all the 4 fermionic modes turned on as condensates, you expect those states to break the SO4 and only 5 over 6 of the entropy. So if you look at the entropy in the Stromer-Javafa, 5 over 6 and on the square root are spherically symmetric, and 1 over 6 actually correspond to the fermions which break the spherical symmetry. So the question I'm asking is not about geometry, it's about, again, going from Stromer-Javafa to this kind of states. So
I'm just not sure that the statement that you made, I believe it's a weak coupling statement about the states in the CFT that at 0 coupling are BPS. What might happen is we know that if you compute the partition function in the free theory versus the index in the free theory, we know that the partition function is much bigger than the index. So I think this suggests that, there's a lot of lifting of states, like states that were BPS in the limit of free coupling might not be BPS in the limit of strong coupling, even though the index remains the same. So it might be that the states that you're talking about might get lifted. I don't know.
Yeah, no, that's quite unlikely, but okay, we can talk about it later. Sorry, I'm
Yeah, no worries.
eating up the time.
Good. And for my final point, the final point is that one can do a very similar computation for near BPS black holes in higher dimensional ADS. So this was in flat space. One can also do this for, let's say, black holes in ADS5. Those 1/16th BPS black holes have received a lot of interest lately, and one can predict the density of states of primary operators that are close to being near BPS, and one finds a very similar looking spectrum, a large degeneracy of BPS states, and then a gap. Good. So this is how one proceeds with derivation 1. To proceed with derivation 2, you similarly analyze zero modes at extremality, but not only of the graviton and gauge fields, you also have zero modes at the gravitino that exist exactly at extremality, and this is what affects these one-loop determinants. Finally, to proceed with derivation 3 that we had before, one should replace the expansion of the partition function into Virasoro characters by an expansion into super Virasoro characters. And then a very similar argument holds. It's just that super Virasoro characters, the vacuum super Virasoro characters, still dominate. It's just that they're more complicated than the regular vacuum Virasoro characters. But from the 70s Eguchi papers, the vacuum Virasoro characters, super Virasoro characters, are actually known. And they reproduce precisely the same density of states for in 2D CFTs that are 4,4 or 4,0 supersymmetric. And a final comment is that in order to do what Strom and Dreyerwaffe did correctly, one has to take the same limit of the super Virasoro characters as before, and that probes this part of the spectrum. So it's somewhat of a coincidence that the semi-classical trajectory, that this is what Cardy predicted, precisely matches with the tip of the delta function when you take the energy to be the BPS energy. Very nice, lucky coincidence. But this is a way of making the calculation of Strom and Dreyerwaffe a lot more rigorous, because it's applicable now for arbitrarily large inverse left-moving temperatures. Inverse temperature for left movers. So if you take beta left going to infinity, you're now probing this part of the density of states. So you actually have to be careful about the full form of the super Virasoro character in this limit. And that's how you see this delta function. And final comment is the gravitational path integral in the previous examples that were non-supersymmetric were not able to resolve anything about the discreteness of black hole microstates, right? I plotted the density of states, and it was just a continuous function. Now we see that even in perturbation, no worries.
No problem.
Now we see that even the density, now we see that at exactly extremality, we see a discrete set of states that's separated by a gap from the rest of the spectrum. And this is, in some sense, a first evidence that we see of a Hilbert space from the gravitational path integral alone. To have a Hilbert space, one of the basic things that you need is your density of states to be a sum over delta functions. This is a delta function, showing that the coefficient in front of this delta function is an integer is another requirement in order to show that these states actually have a well-defined Hilbert space interpretation, and this is an arduous process of a program called supergravity localization. Okay, so I'll end the lecture for today here. Yeah.
Maybe it's a quick one, but just related to your comment about in higher dimensions with the ADS5 black holes, let's say. I thought that in the superconformal index, you see a cancellation, and if you don't want to see the cancellation, you need to complexify the fugacities.
Yeah,
Is
so
that something similar you have to do here, or?
the superconformal index in n equal 4 superunion hills has been computed as a function of the fugacities. So it's been computed in the grand canonical ensemble. Here, what I meant is that this density of states looks similar when we fix the charges of the black hole. Q, the Q's, and unfortunately, computing this index for a fixed charge is a very arduous endeavor that no one has done. So this is a prediction about the degeneracy of states in a fixed charge, fixed angular momentum sector. Any other questions?
I have a question about the gap.
Yes.
So if in the gap, so it's linked with what I'm saying. In the gap, you expect to have 0 states completely, or do you expect to have some subleading number of states?
That's a great question. We don't know yet. So here, the evidence that we've provided for this gap was in a perturbative expansion in 1 over g Newton around this supergravity solution. We have further evidence that I might describe in the 5th lecture about the fact that this gap survives when you add non-perturbative corrections. However, we haven't added the full zoo of all possible non-perturbative corrections, so the answer is who knows. In addition to non-perturbative corrections, there's an effect. Well, there might be things that are doubly non-perturbative in 1 over g Newton, like e to the minus 1 over g Newton. And those actually, in some matrix integral examples that are slight analogies to these black holes, can cause leakage from a continuum of states into what's called a forbidden region that has negative energies in standard matrix integrals. And perhaps a similar doubly non-perturbative effect occurs here. We have absolutely no control over it.
The thing which is interesting is, again, if you look at the superstrata, we get exactly this gap. So we could have gotten the gap to be divided by 2. So we could have gotten all the supersymmetric states, which again is a subleading number of the entropy, but still quite a bunch of them.
Right.
And then you could have gotten a gap to be like 1/2 of the gap you get. There's a rather big rather big number of states there, but somehow we didn't.
Right.
And that's so. I guess the way seeing it backwards, what see there's a non-trivial argument that this gap, there's nobody living there. Even if you gotten something there, it would have been quite a strange result. So the fact that we didn't get anything there, even again, it's a very different calculation. Some bubbling solution, some wave equation, which is horrible to solve, and you compute, and it comes to be 2 over n 1 and 5 exactly. So it came exactly to be at the value which you get to the intersection of the curve. So it could have been 1/3 of that, and in each case it would have been smack in the middle of the gap.
Perhaps since you're asking, I can make another comment, which is related to what I was saying earlier. Namely, if you consider this model of JT gravity in this, what happens in this EFT when you add handles, when you consider an path integral over higher genus surfaces, we can robustly show that there are no higher genus contributions to the density of states in this region, which is the non-perturbative evidence I was talking about. You had a question.
Yeah. So when you run this argument with the super Virasoro characters,
yeah,
like with the usual ones, you get the Schwarzian density of states, basically.
With a regular Virasoro, yes.
With the super Virasoro, you get also the discrete part.
Yeah.
Both things, or
you get both things. Yeah. It comes from taking this beta left very large, and then taking the Laplace transform of the formula that was known for the super Virasoro characters. Yeah.
And in another question about this, about the sum over topologies you were just saying.
Yeah.
So, should we? I mean, should we also sum those in the for this case? Like, should we actually consider the curve given not just by the trivial topology, but by summing overall the?
So I would, my answer is that, okay, in toy models, we can do whatever we want.
Yeah.
We could sum and see what we get, see what happens. The thing that I find attractive in this particular supergravity case is that, you know, even if you consider these higher topologies, they give no contributions to the gap and to this degeneracy of the density of states. So the reason why I'm mentioning that is, you know, like if you would have received contributions, you might have worried that those contributions are out of control. So, you know, you might not be sure that it's correct to include them or not. But the fact that even if we include them, they vanish is suggestive that this gap is somehow protected under non-perturbative. Any other questions?
Well, okay, so thanks.
Thanks a lot.